Hello community, it is a beautiful Monday morning. We have a brand new week, so let's start and let's explore today's topic. And I planned to show you this new study here by Department of Mathematics of the Vrije Universiteit of Amsterdam, in the Netherlands, Europe, by the way. Hello Europe! And today, April 14, 2025, they published here optimizing here the power grid topologies with reinforcement learning here, a brand new survey of methods and challenges that they encounter here, because they say, for the power network control in Europe, they found out that reinforcement learning has emerged as a promising approach. And this is what I expect, Department of Mathematics, so far away from any real-world application, nobody ever, believe me, I know this for sure, would trust here or listen to somebody from the Department of Mathematics here for an investment strategy. So we have here a beautiful comparative numerical study. This is the way science should be, no? Power grid reliability, topology optimization, reinforcement learning. Isn't it beautiful? And you see we have the application here of AI agent here for here power line, substation, generator, storage here, bus geography. Beautiful, this is exactly here, and they tell us, hey, this new survey aims to provide here a foundation, a knowledge, a comparison for future advancement in reinforcement learning driven power grid optimization. And this is what I love. This is exactly where I say, yes, this is science. They study, they examine. Department of Mathematics, lot of simulations, and then we discover the strength of this system, and maybe then we deploy this system, And have a look at this study. They have a beautiful comparison here between here all the different methodologies. They have here the algorithms used. They have here the thresholds, whatever about the reward topology. Have a look at this. It's really informative, And this is what I wanted to show you until in the morning, my eyes showed me something completely different, and we have to talk about this, And my eyes showed me here, here, new publication here, challenging technology to serve the public good. And I said, what could go wrong on a Monday morning when I open here my mail, And then here, for the first time, AI is being used at a nuclear power plant in California, Diablo Canyon. And I said, this is something that you want to read on a Monday morning. No, this is really amazing, I have to tell you, especially if I continue here. Some lawmakers, so not all lawmakers, just some lawmakers think that additional guardrails are needed for the future use of AI in the nuclear power plant. And I imagine here this typical lawmaker, highly educated in mathematics, theoretical physics here, computer science, about, 21 to 22 years old, absolutely on top of research academia, knows everything about the power of artificial intelligence. Oh no, maybe you should read the article and you discover here a complete different world. And I was really interested, and have a look at this, read it. And it's really interesting because you have here Pacific Gas and Electric here, maybe a company that is also inclined to have some financial profits from its operation. And they have now here with a new AI startup here, they have now investments, And they say, yeah, this is the first on-site generative AI deployment at a US nuclear power plant. And I don't know how to tell you this, but there is a certain feeling in my heart. When I knew about the beautiful powers of AI, that they have here an AI deployment. So please read here the publications or other sources, whatever you get your hands on, and you will find out, no, it's not, come on, relax, no problem at all. For now, the facility will use AI just to comply here with safety regulations, so nothing in particular that could have some impact, Until you read here by this AI startup company that they will train here the AI on these nuclear words, And I don't know how to tell you this, but if I read here this professional wording, they will train here this AI here to learn here these nuclear words, So I decided maybe I can help them. No, I can be here of benefit for them when they want to train here AI on these nuclear words, So let's open up this beautiful and let's have a look at the latest research. Because there's another study. You have to know, little AI startup here in California, operating here on a nuclear reactor here, first time in the US. If you want to really train here an AI, and maybe you look here at reinforcement learning, you should know that this reinforcement learning post-training amplifies here a very specific mode from the pre-training mixture while collapsing here the other data distribution. And if you say, yes, I absolutely inherently understand all consequences of this, I say, great. This is the only thing that I wanted to tell you. Wish you here high performance. If you say, wait a minute, what do you mean? We depend now on the pre-training and whatever we do here in the post-training, that reinforcement learning, it is just an echo chamber here for one particular distribution mode? Exactly. And they write here, the reinforcement learning, this post-training has improved the reasoning capabilities of our LLM, specifically where we can really verify it easily in mathematics and coding. But why this is working and how this is working is not fully clear. And they say many models that undergo here this reinforcement learning post-training benefit here from the pre-training data. But there's a little problem, these pre-training data users do not have full control over or even know what the pre-training data were if, let's say, Meta did the pre-training of its model. Therefore, making it difficult to disentangle whether the observed performance gain are really from the reinforcement learning itself, let's say for the literature of some safety regulation of a nuclear power plant, or it was already in the pre-training and there's nothing much that reinforcement learning actually is contributing here to this bouquet, to this wide spectrum of reasoning capabilities. So what to do? Well, one team of authors were brave enough to say, we have to train new language models from scratch using known data mixture. And we have to systematically analyze now the interaction among the pre-training data composition and the reinforcement learning algorithm. We should take care about the model scale. We should list all the hyperparameters we use. And we should really examine now, finally here, mid of April 2025, what is happening in this reinforcement learning. And they said, okay, so give them a base model here, pre-trained on a mixture of open source data sets. The authors now apply here very specific post-training to solve a mathematical task. They work here in the easiest case with a binary reward function, 0, 1, correct or incorrect. And then they observed what is happening. And if there's from this pre-training mixture, if the reinforcement learning just picks out one specific data distribution and pushes this one, and only this one. So is it really that reinforcement learning is just an echo chamber? So what is the simplest case you can think of? No? The simplest case, if you do a complete pre-training, this is very expensive. No? You have smaller models, but you want to be as simple as possible. You don't want to have linguistic complexities or semantic complexities. So you go, I just want either I code or I have a natural language. Because code is relatively easy. A more algorithmic step-by-step coding approach. I have a deterministic reasoning process. I can follow in the code structure and the code sequence itself. And it is computationally explicit. I can debugging, whatever. Great. Natural language, higher level reasoning approach would be great for more complex problems. But let's see. So let's do the simplest case. And of course here, for the model, they used now decoder only, a classical transformer, and they trained it here now on specific combination of mathematical coding instruction data. No? And they use open data set. They are transparent. They say, we have here a different combination of different pre-training data sets, and we have now objective function. And for the model policy, pi theta, it is the simplest one. We just have a binary reward function. So everything, the most simple you can think of, no? And then they even have an analyzation, and they go for the Kullback-Leibler penalty term that is used if you compare probability distribution. And they say, you know what? Looking at this, we find here that maybe we can not really have a focus here on Kullback-Leibler penalty because there's a specific case. So let's explore this in more detail. So, as I told you, open source datasets for the pre-training. They start really at the beginning, and they have these document-style corpora, fine mathematic and algebraic stack and whatever, an instruction dataset, tiny GSM, OpenMat instruct 1 and 2, and question-answer pairs. So you see, you can really decide here what mode of operandi the reasoning happens here, or the output is generated, no? Because the output format is one of their major indicators, no? And they say, listen, if the Python code is within a function, like function simple math problem, then we know it was tiny GSM. If we have here a Python code within the LLM code tags and numerical output and numerical LLM code output tags, we know it is from the OpenMat instruct dataset, training dataset, pre-training dataset. Or if I have a natural language answer, you have a box final answer, where we have more or less of a linguistic reasoning, I know it's from the OpenMat instruct too. So you see, you can, in the simplest case, just looking at the output format now in the reinforcement learning output, what happened here from the pre-training stage to the post-training reinforcement learning alignment. Plus, they also do here a pre-training mixture of varying dataset. So they say, you know, we go with this one, but then we also have repeated multiple datasets, 4 times a tiny GSM. No? We want to have here kind of a preference imprinted here on the system. So they try all these beautiful things. And yes, you guessed it, it is Ivory Tower. It is an elite university in the US who has the money to do this. And they also say, but careful, if we do here the reinforcement algorithm, no? What we do, we go with the classical, this is the safe side, we go with a PPO, a proximal policy optimization that we use, and then we go here from Open DeepSeek or 1, you know, since more than a year now, the group relative policy optimization, specific simplified variant where we have not to deal here with a specific value function, value modalities. Great, and then we have an expert iteration, and we run everything in the combination for all the different reinforcement learning algorithms. And we want to really understand what's happening in the simplest case. So, since they have to pay for this for pre-training and everything, they started here really tiny models. No? A 150 million free trainable parameter and a simple 1 billion free trainable parameter model to investigate here. How important is it here, model scale? Are there differences? Are bigger models really better in their complexity reasoning and so on? Yeah. Rope embeddings, positional embeddings, here the different layers, feed-forward multiplier, and the pre-training, as I told you, different varying ratios, 4 times a tiny GSM and 8 times tiny GSM. They really wanted to make sure they have a broad mixture, but a simple evaluation procedure. And then this is what I found. To their surprise, they learned that the reinforcement learning, this alignment now, pushes the model to generate outputs in a format of a single pre-training distribution. So from all the varieties that the reinforcement learning could align, push forward, it chooses only one, a single pre-training distribution, data distribution. For the smaller model, for the 150M model, this was the tiniest code style element. And even they found removing here the Kullback-Leibler penalty altogether did not significantly change this overall behavior. So they found here the first result, and they said here, hey, the smaller models, they favor simpler code-like formats if they encounter mathematical or more complex reasoning problems. And the larger, the 1 billion model, shifted already a little bit towards a natural language output, here in particular the OpenMat instruct 2 style. So this is interesting because it shows us that the more complex model and the model with 1 billion and plus pre-trainable parameter, they are really able here to move now from a simple code-based abstract reasoning here to a natural language-based reasoning structure. And they have different elements here, from grade school math here to more challenging mathematical problems. And they said, if you get the right mode here from the pre-training, you empower here in the reinforcement learning, you can have a positive transfer of reasoning capabilities. So if you have a strong oral alignment here on a grade school mathematical things, and then you go to more challenging, but in the same domain, in the same task orientation, to more challenging mathematical problems, and the model picked up the right data distribution mode for the alignment, for this empowerment, hey, we have really a positive transfer of reasoning capabilities. Now, interesting, they found that this R1 induced the GRPO, this group relative policy optimization, showed a similar distribution preference, which is amazing for me, but more about this later. But also it was less stable than this classical PPO from OpenAI from 2017, with also a performance collapse followed by recovery. So it is interesting, if you have really absolute transparency, you find new behavior here, even in your policy optimization methodologies. Yeah, an expert was not really. So you guessed it already. We are talking about Harvard University, Harvard University, Harvard University, Harvard University, Harvard University, and you have never guessed the last one, Harvard University. Because they say, hey, we really want to understand reinforcement learning fine-tuning, and we don't. It is not well understood. So they came together April 10, 2025, and they say, okay, let's do this. Let's do this study. Let's really try to get the idea, does reinforcement learning post-training amplifies behavior learned in pre-training? Is it just an echo chamber? Or is there really something brand new, this AI emergence of intelligence? Or is this just a daydream? Guess what? Okay, so they say recent work demonstrated that reinforcement learning consistently improves the performance even in small-scale models. However, the underlying mechanism driving this improvement, why does it happen one time? Why does it fail the other time? We do not really understand here what's happening. And they have a beautiful GitHub repo, so if you want to have access to their data and everything, and the examples and the inference and the pre-training, everything is open source, so Harvard, beautifully. You know what? They come to the conclusion the reinforcement learning drives the conversion to one, and only one, dominant pre-training distribution. So whatever happened in the pre-training of your large language model, it has an everlasting effect. And whatever you do in the reinforcement learning, if you thought you would be able to train here this horse new tricks, no. You just have here a conversion to one of the dominant pre-training distribution already at the pre-training scale. So it all comes back to the pre-training. And normally when you get a model, an open source model, you have no idea about the pre-training. So this is really a black box that is even more darker, more black than we imagined, because whatever we do in reinforcement learning is dependent on the pre-training distribution. And they call it the echo chamber effect. So what is the main result? So whenever you further train a language model, let's say a student, using here reinforcement learning, it's like putting it in an echo chamber. Instead of learning completely new methods, which would you expect, no? Because you have new data for reinforcement learning. You have new training data. You spend $1,000 or $10,000 for reinforcement learning. Eh? And now Harvard tells us here, you know what? Reinforcement learning alignments mostly amplify here the way of solving problems it already learned during its initial pre-training. For a student, it's a textbook reading at the very beginning. It all comes down to pre-training, the quality of the data at the pre-training, and you can do whatever you want in the reinforcement learning, helping the AI startup in the nuclear, operating here at the nuclear power plant in the US and California. Maybe you should choose your model wisely that you want to apply it to. So this is now Interesting, because the study would end here, no? This is it. But you know what? You can't stop your brain, no? You say, wait a minute. So if reinforcement learning amplifies what is learned from the pre-training methodology, and we have here really a one distribution setting regarding style and patterns, patterns can be much more complicated, no? Than just code or natural language. What does it really mean, the collapse here in reinforcement learning, to a single pre-training distribution? What would it mean if we go from code and natural language as the only discriminator in our training data set to a more complex reasoning process? Does this mean that also the way a model reasons in general depends on its pre-training data? And whatever you do in reinforcement learning is nice, but you will just amplify one channel of all the possibilities, and this one channel was the one that was dominant in the pre-training data? Think about what it could mean. Because format, if you want, is just like a proxy for the underlying reasoning style, if you think in a higher dimensional reasoning space. And the shift in the format preference suggests that a change in the dominant way the model approaches problem solving. So what if we say we take here the next step? What if you want to write your next PhD thesis, or you are looking for the next ground publication? Maybe do the experiment and go the next step. Because the fact that the reinforcement learning fine-tuning here on the simpler problems lead to a positive transfer on harder problem indicate that reinforcement learning is enhancing something just beyond the output format. No? Because it is enhancing here the reasoning capabilities of this model when benchmarked against AIM. 2024 or 2025, doesn't matter. So there is something happening in reinforcement learning. Yes, it is focusing on this one mode. But it is not just the output format. It is also, and this is what I believe, until the experiment is done, that it might have also an effect here on the reasoning complexity. And I think it is likely improving more general reasoning capabilities than can generalize here to a more complex task. I mean, this is why we do the reinforcement learning. No? And while the format preference is amplified, I hope, or I dream, or I wish for that the underlying reasoning skills are also being refined and improved through the reinforcement learning. But this is not part here of this beautiful study by Harvard. This is just here, this would be the next step. They only shown here that the format preference, because this is the simplest they could do, is amplified. And the next step would be, how can we design experiments to see if the underlying reasoning skills are really be refined and improved to reinforcement learning. I think only then we can really understand how to build reasoning models that really outperform everything else. So here we go. Here we are. Single distribution convergence. This is what we achieve with reinforcement learning. After the reinforcement learning post-training, model tend to produce output predominantly in the format, or if you want in the style, of one of the pre-training distribution, effectively suppressing all the other distribution. If you think about this and you say, hey, wait a minute, we are not going here with with a reward model that also values here step-by-step reasoning capabilities, but we go here with a binary reward function, no? With a binary reward signal, even stronger. So you say, okay, if I only can be 0 or 1, then I understand that here in this process of reinforcement learning, with this particular simplified methodology, I will only arrive at one mode. You know how much interesting it would be to run the same experiment now, not with a binary reward function, but with a continuous reward function. So fascinating to be here in AI. And then the single distribution often corresponds here, and this is interesting, to the most initially performant format in the smallest model. So if you think with reinforcement learning, you teach the AI something new, you improve the reasoning capabilities, you can ignite something that was not there before, this might be a mistake. Because if Harvard tells us, hey, this single distribution often corresponds to the most initially performant format, this means that it's really all depending here on the first pre-training, on the quality of the data of the pre-training data sets and what evolved here in the pre-training here as the first mode of performance. And this initially most performant will then be, in the course of reinforcement learning, be just amplified. Interesting to think about this. So, reinforcement learning based fine-tuning or post-training fine-tuning would be a supervised fine-tuning. So, reinforcement learning based post-training acts like an amplifier, consistently driving a language model toward a dominant output distribution present in its pre-training mix, and a particular distribution selected depends strongly on both the scale and the data composition in our pre-training dataset. I think this is so fascinating because it means the only thing that really matters is the pre-training. And we as user, we have no idea about the pre-training because this is the most expensive part that every global corporation keeps secret. And now we understand why. But you know what? An even simpler experiment will be, so even with natural language, think about it. You have different style in natural language, no? Of explanation. You can have a brief explanation or a more detailed explanation. You can go and run this experiment like Harvard did with a formal or more informal explanation. So although Harvard does not delve into these finer stylistic nuances, it would be really the next step to do this in the next experiment. So there's work waiting for you if you want to make yourself known here in the domain of artificial intelligence. No? And the same is true for code, because code also have different styles, no? Different algorithmic styles to be more precise. So you have brute force or more optimized algorithms, real clever solution, or just, put together one simple idea, next simple idea, next simple idea. And then we try it. And sometimes here Cursor will tell us after 15 times, clicking here, optimize, maybe we come to a solution that is not the optimal, but it is somehow working. No? Imagine what we could design experiments here. No? But again, Harvard does not deeply analyze here the algorithmic style within the code outputs, but it focuses here more on the broader code versus natural language format distinction. So I would say this is really the first kind of an experiment we have to do here to really understand what is going on in reinforcement learning. And I know that everybody says, hey, we have no resource. You will need 10,000 NVIDIA H100 GPUs to really start here with a pre-training. And the right pre-training and a high-quality data pre-training. And yes, there's a reason why everybody is focusing on supervised fine-tuning and reinforcement learning. But we have to invest in this. I don't know. Take all the every university in the US or in Europe or in Asia. We have to get here to the bottom and try to understand here the real mechanism. And if we just scratch on the surface and we stay within supervised fine-tuning and reinforcement learning, yes, I know this is the easier path, But if you are into AI research and you really want to understand, deep dive into this, to really understand the core principle, why AI works and how to optimize AI. Yes, maybe you subscribe and maybe in my next video I have another idea. My goodness. So maybe you say, no, never ever again. I'm happy with my supervised fine-tuning. Then in this case, do not subscribe. It is all up to you, but it would be great to see you in my next video.